is. Thanks a lot, everyone, for coming. This is Introduction to Amazon DynamoDB. You will be hearing from 3 of us today. So I'm Dave Lang. I'm the product manager for DynamoDB. You'll also be hearing from Eric Nadalon, who's the co-founder and CTO of Nexmo, and Eddie Dingles, who's the technical lead at Earth Networks. So I'll give you just a quick overview of what Dynamo is, why you might care, what we were thinking when we built the thing, and then these guys will talk to you a bit about how they're actually using it in production. So DynamoDB was really born out of a lot of what we learned coming from 2 different directions. One was running really high-scale, high-performance databases to serve Amazon.com. And we had very stringent performance and scale requirements there, and we learned a lot about it. But we also learned a lot about how to run a service just by virtue of AWS. We learned a lot of, you can have a great technology, but if it's a bad service, it may not go anywhere. And we've been really happy with the response we've gotten. We've been really grateful. Dynamo is actually the fastest growing service that AWS has ever launched. So we're really appreciative of the response we've gotten from the developer community. So what is the thing? So DynamoDB is a fully managed non-relational database service. And when I say service, I mean you access DynamoDB via API. You're not worrying about hardware, software, any of that stuff. You're just using the database really as a service. It's built exclusively on top of solid-state drives. We actually have a custom hardware stack tuned specifically for the performance and scale needs of Dynamo. It's designed to operate at any throughput rate with consistent low latency performance. And there's no limit to the amount of storage that you can put into your DynamoDB table. And when we were building it, we had a few design philosophies or tenets in mind. And one, and this is really something we learned through AWS, is we really wanted this to be a really, really easy to use service. Like we've had really advanced and awesome technologies before that were hard to use, sort of internally. And we noticed that as that technology propagated, we would get a lot of pushback if the learning curve was high. It's not efficient if you build something awesome that everyone has to learn how to use and spend a ton of time on that step. So we wanted it to just be ridiculously easy to use. We wanted consistent high performance. It's not that hard to build something that is really highly performant sometimes, but it's really hard to deal with a database that is only performant sometimes. Monday it's great, Tuesday it's not great. That's really hard to deal with, and we wanted it to just be extremely consistent, a very, very tight band around the range of latencies. We also wanted it to be an extremely highly durable and highly available service. Again, you can get high performance if you're willing to, pretty easily if you're willing to compromise on durability and availability, but we really, really didn't want to do that. We wanted this to be a rock solid, highly available, very durable service, and then on top of that, get the performance. And the last design tenet was that we really wanted this to be a service where scalability was our problem. Scaling is hard. We've had to do it a ton at Amazon. We've learned a lot, and it just seemed really inefficient to ask everyone else to learn how to do it themselves to use our services. So we wanted to build something where scalability was something where you tell us what you want, and we just sort of figure it out for you. So Dynamo has a flexible data model. It's a non-relational database. There's no fixed schema. And data within the database is stored as a series of key value or key attribute pairs. And the way you access it is, so every DynamoDB table has a primary key. And that primary key can either be a single attribute hash key or a composite hash range key. So a single attribute hash key basically turns Dynamo into a massively scalable, low latency hash table. The composite hash range key, that'll give you something that lets you run range queries within a hash bucket. So for example, you could say, make my hash key the user ID and make my range key the timestamp. And now you can run queries like, hey, give me all the records for this user between these 2 time periods. We support multiple data types. We have string, number, and binary. We also, so I mentioned that we store attribute value pairs. The value can be a single value, like a single string, or it can also be a set of strings, numbers, or binary data types. We also support strong and eventual consistency. So and some of you know about this, some of you don't. Eventual consistency is basically, if you do an eventually consistent read, for example, you're accepting the risk that your data is just slightly stale, that it's not guaranteed to be the most recent thing that was written into the database. And if you're okay with that risk, there are a lot of performance and cost benefits that you can get in exchange. You can really, really reduce costs pretty drastically if you use eventual consistency, and you can have an even more highly available service. But knowing that the data might be slightly stale, that can be a hard thing to program around. So a lot of people prefer strong consistency, where you're absolutely guaranteed to get the latest data that was written into the database. So we learned that running some eventually consistent databases both externally and internally at Amazon. And so we decided with Dynamo we would just offer both. So you have the option at the API level. So when you do a read from Dynamo, you can actually specify if you want the guarantee of strong consistency or if you're willing to accept the risk of eventual consistency and get the cost benefit. So we offer both. So I mentioned that we wanted this to be a very highly available and highly durable solution. And part of how we managed to do that with Dynamo is that we made it a multi-AZ or a regional service. So essentially when you create a table in Dynamo, we automatically spread the data in that table across multiple availability zones. An availability zone is, you can think of it like a data center within an Amazon region. And we actually won't acknowledge a write as successful to Dynamo until it's at least on disk in at least 2 different geographically distinct availability zones. So we spent a lot of time doing the math on this, and we believe we've come up with a pretty nice blend of very, very high durability and high availability while still maintaining the latency. So let's talk a little bit about how this used to work for us and for others before Dynamo. So suppose that you needed to create a database to support your app, and that database needed to be able to handle, say, 1,000 writes a second, or 10,000 reads a second, or whatever scale is appropriate for your app. Once you had figured out what you needed, in most cases you would have to go and launch on a fairly extensive and potentially painful exercise of figuring out how you achieve that performance. You would have to think about what hardware am I going to buy, or if I'm buying an instance from Amazon or another provider, what instance type, what combination of memory and CPU and hard disk specs are going to give me the actual performance we want. And so this is great, and a lot of the things that you can buy are really great general tools. But if you're looking specifically for database performance, the problem that we saw when we were designing Dynamo was that it felt like kind of an inefficient way to communicate with our customers. It was to ask them to tell us all this stuff on the left when what they actually wanted was the stuff on the right. And so we knew what our customers were basically going to be coming to us and telling us, hey, here's what we think we need to achieve some goal that we're not going to tell you about. And that just kind of made it hard to serve our customers well, and we didn't want to do that. We basically wanted to say, forget the stuff on the left, just talk to us about the stuff on the right. We have a ton of experience with implementing massively scalable databases. Why would we make you learn how to do that? So tell us what you're trying to achieve, and let us figure out the underlying implementation. And out of that came something that we call the provision throughput model, where we basically want you to tell us the performance you're trying to achieve, which is the goal, and then just forget about the rest. That's Amazon's problem. That's what I meant when I said scalability is our problem. You do not think about instance types, you do not think about hard disk space, just tell us the performance you're trying to achieve. So when you create a table in DynamoDB, the way it works is you create a table either through the management console or via API, and you basically tell us, I want the table to be able to handle this much write throughput capacity and this much read throughput. So for example, I might say, I want a table that can handle 10,000 writes a second and 20,000 reads a second. We don't even need to know about storage. Dynamo has no limit to storage. And at this point, your job is done. It is now Amazon's job to figure out very, very quickly, within seconds or minutes, how do we provision machine resources behind the scenes so that you achieve the throughput that you just asked us for. And you are absolutely not locked into that. I want to be very clear about that. Dynamo is scalable, but it also, you can change the scale on the fly. So you provision your table, I want 10,000 writes a second. Great, we give it to you. The next day, you realize you need 20,000. Sorry, see if you could just hold it to the end. We'll try and, actually, I did forget to say that. We will leave time at the end for questions, but if by any chance we run out of time, we will be hanging out in the hallway, so we'd be happy to take all questions. Sorry, I just don't want to run into their time. With Dynamo, you can change your scale on the fly. So you just go back into the management console or send an API call and say, okay, I had 10,000 writes per second before, now I would like 20. And behind the scenes, Dynamo will figure out how to make that happen without downtime. It'll just spread your results, your data over more machine resources, provision more capacity for you, scale it up, and it just kind of works. And you pay by the hour for the provision throughput capacity that you've asked us to provision. It's a very similar model to an instance in that you pay by the hour for the capacity of an instance, except we're asking you to specify the throughput capacity instead of specify the instance type. And again, you don't have to tell us anything about storage. You put storage in, we charge you for it, you take it out, we don't charge you for it. So here's an example of how you would do it. So this is our management console. So if you were to go in and create a table in Dynamo, this is the first thing that you would see. And we're basically asking you what's the name of the table, in this case customers, and what's the primary key that you want. In this case I picked a hash table with the hash key being customer ID. The second step would be how much throughput capacity you want. In this case, I'm picking up capacity to do 10 writes and 10 reads per second. And at this point, we now have all the information we need to create the table that you've asked for. There is a third step I don't have a slide for where you can optionally set up throughput alarms so that if my throughput gets close enough to my provision capacity, we can send you an alarm and let you know that you might want to consider raising it. I didn't include a slide about that, but it's really a two-step process. It's the only required steps. And at this point, you have a table. We actually have a video floating around the dev team of someone's 6-year-old creating a massive table just because this is all it takes. I wasn't allowed to release it, so sorry. So yeah, and again, I mentioned it before, you can change the scale with a click of a button. There's a similar wizard to the one I just showed you where you just go back in and say, oh, I just want to change those two numbers I set for throughput capacity, and then you get it. So one of the problems I mentioned that Dynamo is designed to solve is just scaling the database up and down and making that just work and not spending all your time on it. So that's one of the things we're trying to solve. Another thing, or another benefit of Dynamo is that we try to make capacity forecasting less of a scary, painful exercise. And I imagine that most people in the room have been through capacity forecasting. We all got it wrong. It was only a question of like, how wrong did we get it and in which direction? It's a difficult process. There's a lot at stake. And it takes a lot of time. Like if you want to prepare your database to run at 10,000 writes a second and you're doing it yourself, and you're running your own software, you really have to go and do it to make sure that it works and run extensive tests on the various scenarios at that scale. And it's a difficult process. So there are a couple of philosophies that you can take when you're thinking about capacity forecasting. So one is to take sort of a timid, conservative approach. Just basically provision way more than you think that you'll need, or at least test at that scale. It's a nice approach in terms of customer experience because you can really be sure that it will work in the scenario that you're worried about, or even far beyond the capacity that you think you'll need. So that's great. It's an expensive way to go. You often end up buying too much capacity. You certainly have to spend a lot of time testing at higher scale if you really want to be sure that it's going to work. So the conservative approach is great for serving customers and ensuring a good experience, but it does come with a cost. Alternatively, you can take a more aggressive approach and really try and cut it close to the line. Try and provision only what you need, which is a really cost-minimizing way to go if you're right. And if you get it right, great, you saved a ton of money. If you're wrong, it's very, very risky. You may, especially if you're wrong in the direction of not having enough capacity, you may find yourself in an emergency situation where you need to scale up very, very rapidly. And you've never done it before, and you don't know if it's going to work. It's a scary place to be, and it puts your business at risk. So we're very familiar with this problem at Amazon. This is sort of a typical holiday traffic pattern we might see on Amazon. It peaks towards the end of the month. You can probably guess what months I might be talking about. And so we would, weeks or months in advance, spend a ton of time thinking about what this curve might look like, and then coming up with a capacity model that'll work for us. Excuse me. And typically what we would have to do is provision a capacity that is a little bit above the peak that we think we're going to get. We want to make, we take the approach in Amazon, we really want our customers to have a great experience, so we don't want to cut it too close to the line. And so, this is years ago what this would have looked like for us. And there's waste. Like everything between the capacity line and the actual traffic line is capacity that technically we didn't need. You could argue about whether or not it's wasteful, but there's definitely an opportunity to optimize there. With DynamoDB, we can cut it a lot closer to the line. The ability to go into, if you were trying to scale a database from, say, 100 writes a second to 1 million, like on your own, running your own software on your own instance, that is hard. Strange things happen at high scale, like unexpected things. You have to spend a lot of time preparing for that. With Dynamo, you basically go into the management console and click a couple of buttons and just wait for us to finish our work, which won't take very long. Which allows you to really ride the wave a little bit more closely to minimize costs. And it's also a really important point that in addition to minimizing cost, you're also minimizing risk. Your forecast will be wrong. It's just a question of how much and in what direction. And the scary thing about a forecasting process where if you really need to significantly change your forecast, or change your capacity to a level that you haven't been before. I mean, that can be a multi-week or a month-long project if you're trying to figure out how to build a distributed system that will operate at that scale. So DynamoDB helps in two ways. One is that it brings your forecast window in a lot. The fact that you can change your capacity in minutes on demand, as opposed to having to sit out, plan the process, and maybe take a week to do it, that means that if you're wrong, you can change within minutes. That means that you can cut it closer and be even more aggressive about optimizing for cost. The other advantage is that if you have a growing app, you're by definition continuing to hit scales that you've never seen before. You're doing it for the first time over and over and over and over again. Dynamo is a service that is explicitly designed to reach massive scale, and we do it all the time. So the first time that you're doing it is the 100,000th time that one of our customers has done it. And so you don't have to spend as much time worrying about whether or not you have a system that can even achieve that scale. You get to leverage the experience and the code and the fact that Dynamo has a team that does nothing but eat, sleep, and dream about scaling and performance problems, and leverage that experience for your app. And we do this because a lot of the value of Dynamo is that we're just taking a lot of stuff out of your hands that you shouldn't have to worry about. And scaling without downtime, sharding, security inspections, software, just a lot of the stuff that, I mean, this is stuff that doesn't, in almost all of your cases, this is not going to set your database or your company apart. The ability to scale a database behind the scenes is more of a minimum requirement than something that's going to make your business successful. Part of the goal of Dynamo is that we really wanted to take a lot of this out of your hands and just say, look, we've got it. We do this all the time. It's more efficient. Like, one of the most important economies of scale that we have is expertise. And we can sell you that and let you just sort of focus on your application. And that's really a very important design philosophy for us. We really wanted to build something that would just let you focus on your application and not focus on building the database. I mean, actually, I just want to go back a slide. Everything on this, I was at a startup before coming to Amazon, and everything on this list, this is a list of engineering hours that you did not spend building your application. And that's really painful. And we really wanted to give that back to you. That's why we built Dynamo. I also wanted to make a quick announcement. For those of you who didn't see the keynote this morning, Amazon Redshift launched today. It's a really, really cool service. They've been working on it for a long time. Congratulations if any of the Redshift guys are here. I know they've been working really hard on it. It's basically a massively scalable, high-performance, and very low-cost data warehouse in the cloud. It's a columnar-based database. It's really cool. And it's cool for Dynamo customers for a couple of reasons. One is that we've had a very frequent request from Dynamo customers. It's great that we can ingest and read and write data really, really fast and at massively high scale, but we also want analytics, and how do we do that? So the fact that Redshift even exists is a big win for us. But we're also very happy to announce that we already have an integration with Redshift. So Dynamo customers can create a Redshift instance, run a simple command like this one, and basically say, take all the data that's in my Dynamo table and just pass it over to Redshift, and then start running your analytics there. So this is the extent of what you need to know to operate the integration. So we're really happy about that. So that's all from me for the moment. I'm going to pass it over to Eric, who's going to talk about Nexmo and how they use Dynamo. Again, we'll be hanging around afterwards for questions. So if by any chance we run out of time, we will be hanging around. So we'd love to talk to you. Thanks. That next one, the right one. The middle one doesn't work.
Okay. Hello, everybody. So I'm Eric. I'm a co-founder.
Oh, that's okay. Don't worry about it.
No, it's okay. Nexmo. So I'm here today to talk about our experience with SimpleDB first and DynamoDB. So first, a quick overview of Nexmo. So we are a global SMS API. We can deliver messages to 200 countries using a direct-to-carrier model. So basically, we are the last hop before the mobile network. We also offer a long virtual number in 16 countries, so you can do two-way messaging. We have three types of customer: application developer or OTT player. So they use Nexmo for two-factor authentication and P2P communication. So we have enterprise people like Airbnb to send a notification globally. We also have a reseller, so if you are using today one of those guys, so there is a high chance that your traffic is already going through Nextmo. So you might test our service. It could help us to reduce your latency and increase the quality of delivery. So here, our challenges. As you know, SMS is short, and the volume is it could be quite high. So in the last 6 months, we store more than 1 billion records, and we are adding more than 5 million a day. And we wanted to actually offer more online services to our customer. And one of the most common questions to our help desk is, what is the status of my messages? So in order to fulfill their requirement, we wanted to make sure that all messages are searchable in near real time after submission. And also that the search response time is agnostic of the volume. So we have 2 types of query. We can search for a given message ID, or we can search for an account, a number on a given date. So one more thing to mention, in our case, we have a ratio of 1 read for 10,000 write. So we are mainly writing and pretty much never read, and which is probably very unusual. So now a quick overview of our messaging platform. We have incoming traffic going to one of the hubs, where we can authenticate and authorize the request. Then, depending on the destination, we route the message to one of the gateway. So a gateway is pretty much a protocol adapter dealing with the final carrier, and then it's delivered to the handset. So every component on the platform generates logs to capture information like the sender, the destination, the price, the cost, and the status. And every component also have a log reader putting messages into a local queue. On the other end, the log tailor is consuming the message and actually doing 2 things. So one, it kind of generate real-time aggregated report, so you can go online and see you sent today 10 messages to AT&T, for instance. And the other task is actually to make message searchable. So we started using SimpleDB, and then we actually moved to Dynamo. We ran the two systems in parallel for 6 months, and we stopped using SimpleDB this summer. So what is interesting with Dynamo is actually you can, like Dave mentioned, you can set the write throughput very high. So what we did, we put it a few thousand messages per second during a couple of days, so we were able to re-import the data we had in SimpleDB. So then we had the 2 systems with the exact same data, and then we were able to compare and to measure performance during a 6 months period. So let me give you more detail about the SimpleDB use case. So we started 18 months ago with SimpleDB with this kind of setup. So when you send an outbound message, it includes several records. So one is the submitted message called MT for message terminated. You have one record for the intermediate delivery receipt and one record for the final delivery receipt. In order to improve the write throughput, we had to manually partition every table using 50 domain. So why 50? Because there is a 250 domain limit per account. So when you search for a given message ID, it's very simple because the message ID gives you which partition to look for, then it's just a direct read. And now if we want to do, If we want to do a more complex query, for instance, we want to search messages sent for a given account on a given date. So because of the partitioning, we need to run multiple search queries in parallel. So like in that case, 50 threads running concurrently. So once we find the matching IDs, then we go to the other table and retrieve the information and then rebuild the final result. A year ago, we have been approached by the Amazon product team to actually test Dynamo. So it was actually an interesting move for us because we were reaching actually the insert limit with SimpleDB, and since our volume was going up, the delay to make a new message searchable was getting bigger and bigger. And so DynamoDB makes the partitioning transparent and solve the right throughput as well. So however, you need some time to define an external index for specific search query. So let me look at the previous use case now in the DynamoDB context. We still have the 5 main table, but we don't need to worry about the partitioning because it's done behind the scene. But we need to create another table for our index. So our index includes a composite hash, so including the account ID and the phone number, and then we use the date as a range. So in a kind of regular SQL, the query will look like that. So select ID from empty, where account equal and phone number equal and date equal. So this thing will be translated into Dynamo using the Java API with the following code. So basically we create a condition object. So it's so using the date range between 2 dates, and then in the query you put the hash key and the condition. So if now we run this code, it's more simple because we first just query the index, so there is no parallel search anymore. So we retrieve matching IDs, and then we go to all the other tables to rebuild our result set. And that's it for me. And feel free to test our system, and if you want to get extra credit, feel free to text your email at this number, 12675465 AWS. Eddie? Thank you.
All right. So hi, I'm the technical lead at Earth Networks. So my name's Eddie. Let's get to the next slide. And what I'd like to talk to you today about is how we at Earth Networks are using DynamoDB. Specifically, what I want to talk about is how we used it to do consumer-level lightning alerts on our mobile platforms. So first, a little background. Earth Networks gathers and analyzes global atmospheric weather information. We also have our own proprietary lightning network, which we can use to locate global lightning anywhere in the world with a fairly high degree of accuracy. And one thing to note here is that lightning is a very good indicator of severe weather. So for example, lightning will occur before tornadoes and stuff like that. So Earth Networks is also the owner and operator of the WeatherBug brand. So we have a presence on mobile, desktop, and web. And so into what we were going to do with DynamoDB, we actually got a problem from our CEO starting at the beginning of last year to actually take what we've done in the enterprise space, which is deliver lightning alerts, and actually bring it out to a consumer scale. And what he wanted to do was deliver lightning alerts based on users' GPS locations on their mobile platform. And this is actually a very fun problem. If you really think about it, we have around 6 million mobile users who are all moving about, providing their GPS location to us so they can gather weather information. And then we have a global lightning network which is producing millions of lightning strikes a day across the planet. And what we want to do in almost near real time is put all that data together and for every single user provide lightning alerts to them. Now, when we came to this, we actually had a number of constraints on the problem. One is we had a decently sized user base of about 6 million users, and we have about 100% year-over-year mobile growth. The other thing to note is that we needed a very flexible solution which could scale with changing conditions. So for example, lightning is very different day to day, and I'm sure you see it across the US. When there's large storms, you may see 10 to 15 times the amount of lightning data in the US alone. The other piece is, depending on where the storms are, our user base and access to the system is very different. You know, if you have a storm in Montana where we don't have a large user base, then we're not going to get a lot of reads into our system. However, if it's in New York, the read throughput is going to be very high. Now, when you talk about alerting, speed is paramount, right? So the quicker we can get the information out, the better. However, we can't sacrifice accuracy either. So we need to both have speed and accuracy. And in terms of alerting, that really equals safety. Additionally, we got a couple other constraints that came in from the business side, which I'm sure we've all had before, which is basically they wanted a quick time to market. So we got this in at the beginning of last year, and we wanted to deploy before basically the lightning season started in the US in about March. And the other thing is, we had done this on an enterprise scale, but now we're going out to 6 million users. So we were rebuilding a platform where really we needed to drive the cost of ownership down to account for sort of the less money you receive per user. So when we got the problem, we actually broke the problem down and created sort of a 3-tiered architecture that we wanted to use. And what we looked at is we were going to have a back-end management tier for actually moving the lightning data into the system. We were going to have a front-end web tier, which was going to take in the user's request. And what we really wanted to build was a fairly scalable middle tier that did our spatial intersections and spatial queries and business logic around this. And one of the things we did is we prototyped against a number of systems in this middle tier. So what we first looked at was SQL Server 2008 R2, which supports spatial data types. And what we were able to do is get a fairly moderate throughput per instance out of it. And for us, the engineering cost of working with MS SQL is very low. So I should preface it by saying that we're a Windows shop, so we do ASP.NET applications. Our DBAs support MS SQL. So this was sort of in our wheelhouse. We've worked with SQL Spatial before. So the engineering cost was low. However, the number of instances we would actually need to deploy to support the consumer scale that we wanted to do was going to be very high. It would actually drive the cost of ownership up. So then what we looked at is, could we drive that cost of ownership down by switching to something like MySQL? So MySQL has the reduced licensing costs. However, like I said, we were able to do this, and we were able to get a moderate throughput, but this wasn't really in our wheelhouse. In order to really productionize this, we would sort of have to do a lot of engineering work in order to get sort of the high availability DB mirroring. And also from an IT perspective, since they're not set up to support it, we'd have to deploy or basically deal with the human resourcing issue. Another thing we've done before at Earth Networks, specifically for enterprise, is done custom quad trees. For anyone who's dealt with spatial stuff, this is really just a spatial data structure that you can work with. It can do a very high throughput in terms of spatial queries. However, you have to handle all of your HA, all of your consistency. And so, you know, anybody who's worked in Amazon for a while knows you got to move this across at least multiple AZs. You're going to have to handle consistency between each of the instances you're going to be running. So when you look at the cost of ownership of that, it's going to be less because all you're going to be doing is managing the instances and without managing the licensing. So we still didn't really like that solution at all. We continued looking at Memcache. Memcache actually has a very high throughput. I mean, it's basically an in-memory hash map, so you're able to query it very effectively. And the cost of ownership isn't too bad. However, it didn't really work for what we wanted to do. We had a large set of streaming lightning data coming in, and Memcache is really more of a reactive system for us in that sense, so we didn't really want to look at that. And around this time, DynamoDB came out, and so we started looking at that as a middle tier solution. And what we found here is, in terms of scalability, we can just turn a knob and crank up any throughput we want. And the other thing, in terms of engineering cost, it really is that simple to start working with it. We pulled it down and were able to prototype the system within a day. In terms of making the system production and supportable, your IT staff doesn't need to actually learn a whole bunch of new stuff. It's very easy for them to interact and work with the system. So this is sort of what we actually did, kind of give you a little background on the solution. We have the streaming lightning data coming in. What we're doing is we're taking it and we're geo-hashing it. This is a way of taking a latitude and longitude and reducing it down to a single key. All right? We then take like keys together and we group them into buckets. Those buckets become items inside of the DynamoDB table. And basically it's the responsibility of the backend system for maintaining this sort of work inside of DynamoDB. On the front end, we have a front-end web tier, which is actually bringing in the client request and decoding it. So in comes the client request. with a latitude and longitude. We take it and create a set of geohashes that we need to query against DynamoDB and make that query. Now what's important to realize here is that DynamoDB isn't answering the full question. What we're using DynamoDB to do is actually do an exclusion query. So we have all the lightning data around the world loaded into DynamoDB that we would need to query against. When the query goes in, the client's only going to bring back the lightning data which is relative to them. This will prune out a large percentage of the lightning data in the world. Could be 90, 95%, up to 99% of the other lightning data. Now the front-end web service, we still wanted to do additional pruning before sending this back to the client. And I'll actually show a video at the end that shows really how much lightning data can be localized in a single area. But the front-end web tier actually does doesn't use trigonometric calculations. So anybody who's worked with spatial data has worked probably with greater circle calculations. And those are fairly expensive to do. They involve trigonometric operations. So once again, the front-end client just does an exclusion by using geometric calculations to actually prune out, once again, the data that isn't relevant before sending it back to the client. At which point we send a subset of the data back to the client. The client itself will do the actual spatial data, actually compute the actual spatial distance, and produce the alert. So once we deployed this out, we deployed it out to our iPhone and Android clients. And it was actually fairly successful. But what we found is we were provisioned far above what we would actually consume. And a lot of this occurred because of what I talked about earlier on with we would have spikes in both weather events, so spikes in the amount of lightning data we receive, as well as spikes in, depending on where the weather was, the number of reads we would get. And these spikes could be 15 to 20 times above what we needed. But because it's difficult to predict when they're going to occur and where they're going to occur, we didn't want someone sitting around scaling up and down DynamoDB on a daily basis. So we decided that we were going to auto-scale DynamoDB. And this is fairly similar to EC2 auto-scaling in terms of a concept. So what we did is we actually deployed a set of instances to manage our DynamoDB tables. And this can be done through the AWS SDK with simple REST calls, basically. We monitor every single table, and what we're doing is we're actually calling in to get the actual provision throughput. We're then calling into CloudWatch to get the consume throughput. If the consume throughput reaches a certain percentage of our provision throughput, we will programmatically scale up DynamoDB. And what this allows us to do is handle fairly large storms. So for example, like Hurricane Sandy, we were able to scale up through that event and then scale down the following day. However, there is another case that occurs where you can actually get throttled, and this normally occurs when the event is more local. So for example, with tornado events, where you have a tornado event which occurs around a major city or something like that, you'll get an immediate spike based on people who are hearing these on the news and want more weather information, so they'll jump in. And what we found is that CloudWatch is a little slow with DynamoDB. So DynamoDB doesn't support detailed monitoring at this point. It supports 5-minute monitoring, which basically means you're going to react about 10 minutes late. So what we wanted to do is make sure, since it's an alerting system, we scale very effectively if we ever see any throttling events. So we create an additional DynamoDB table, which is a metric table. That metric table is actually monitoring all of our other tables. And one of the fields that it's monitoring is if there's any throttling on reads or writes. If any of those occur, we'll react and scale the table as well. I have up here that we independently scale read and writes, and this is true, but there is a caveat to this. So when you're scaling up, you can independently scale with no issue. However, there is a limitation on how many times you can scale down your table during the day. What you want to do is scale, which is 1. So the limitation is basically 1. And it's really one or the other or both. So you can't do a scale down of reads and then 5 minutes later do a scale down of writes. So those two need to occur at the same time. And the way we actually handle it is we have a fairly consistent user load on most of our tables due to basically the standard way people use load. Just like the Amazon slide of it daily going up and down, we have the same thing. So we actually have an interval which the services will look to scale down the tables, and at that point it will make a judgment on how far down it should go based on the current consumed capacity. So I just want to talk about what our experiences are, because after we did this consumer lightning approach, we've actually rolled out DynamoDB to a number of our other properties. We use it to back our forecast data at this point. We use it to back some of our observation data at this point. So we really are starting to use it across our whole data center. One thing is it is extremely easy to provision, and it's extremely easy to get into. You can change the provisioning whenever you want and very effectively. So if you want to get in and try it out, it's definitely easy to do. One of the things we love is the built-in consistency, and it's region-level consistency, right? So with like Memcache or Elasticache, you're dealing with AZ consistency. Here you got region-level consistency, which is nice, especially when you're talking about having your applications be highly available. The other thing is it's scalable. You just turn the knob and you're going to get more throughput, right? So if you have a weather event or if you have anything like that, you just keep asking Amazon for more and they'll keep giving you more. Lastly, it's highly available, which I sort of already touched on with the consistency, but basically since it's a region-based service and non-AZ based, you're going to have much better high availability within a region. Now, that being said, there are some things we want, and one of the things is, well, for sort of these first two are connected. So we want DynamoDB to actually span across regions. And the reason for that is, and it can be done in really two ways. One is we can have an automated failover between regions. So for example, we run in the east, but we need to fail over to the west for some region. You can think of this as a failover partner in terms of like your standard DBs. Ideally, though, what we'd prefer is that DynamoDB itself actually scales across regions. So just like it scales across AZs and I don't have to worry about it, I would like it if it would just scale across regions and I wouldn't have to worry about it. So I can have a consistent view in both my east region and my west region, route traffic to either of the regions, and they're always going to get the same result. As talking about with auto scaling down, like I said, the 1 a day is a fairly significant limit. So if we can get that extended, that would help. Lastly, there's an item size limit of 64K. There are a number of workarounds to get around this limit. Actually, the best workaround, which actually is thanks to Amazon, when DynamoDB came out, it didn't have the binary data type, so you're pretty much stuck with strings. And you can get those strings fairly small, but really with binary data, you can pretty much crush your data down as far as you can get it. Now, that being said, getting any more limit would be of use. So what I'd like to do now is just show a quick video. And this is sort of the application in action. What you're going to see is, this is around Indianapolis in a particular lightning event. So all of those colored spots on top of the radar are actually individual lightning strikes. And as the storm moves in, on the right side is our iPhone client, which is querying in to determine where lightning is relative to the person's location. So as you can see, there's a significant amount of lightning data. As it comes in closer, we're able to react to it. So that's it. Thanks for listening. I guess we're going to take questions, and Eric will come up and join.